Hello and welcome to my applied presentation for graph theory. Today we're going to be talking about the stable matchings algorithm, and it's in section 3.2, and it talks about an ideal way to match n men to n women. There's actually no cap on the value of n to make this work. The only thing that we restrict for this algorithm is that the number of men and the number of women is equal. The kind of caveat with this algorithm, again, the way it's presented, it doesn't have to be this way, but the way it's presented is a very sexist algorithm in the sense that it allows the men or I guess it requires the men to propose to the women, and based on a set of rules, both for the men and women, but also in the sense that it assumes that men are only proposing to women. So there is that little caveat with the proposal algorithm. But the idea here is, can we take these n men and these n women and pair them off in a way that produces the best possible pairing? And I'll talk about what we don't want, more so than what we want almost, as we get into some of this. So we consider a pair, again, very sexist, to be man Y and woman A, and they are, in terms, attracted to each other, more so attracted to each other than either of them are attracted to anybody else. And that would give us our stable matching that we want. The thing that we're trying to avoid is the unstable pair, in which an assignment gives man Y woman A and man X woman B, but these two actually are both more attracted to each other than they are their assigned mates. Okay, that's what we're trying to avoid in this algorithm, is the pairing that really makes that really leaves woman A attracted to man X, and man X more attracted to woman A than his current matching. If we can avoid all unstable pairs, we would have what we define as a stable matching. Okay, in a stable matching, it's a perfect matching that results in no unstable pairs. So none of these women prefer a man in another matching at the same time as that man that she prefers being more attracted to her than his current mate. So it's not just that it's going to give everybody their best, their top name on their list. It's more that we don't have the simultaneous situation where these two prefer each other over each of their paired mates. What we use for this is the Gale-Shapley algorithm, or also known as the proposal algorithm. And what it requires as an input is a list of names from each of the men and each of the women, ranking the opposite sex. So in this case, I've got Alvin, who prefers Charlie over Becky, over Donna, over Adriana. Bob, same thing, Charlie, Becky, Donna, Adriana. Cameron prefers Becky to Charlie, to Adriana, to Donna. And Donald prefers Donna to Charlie, to Becky, to Adriana. The women have their own set of preferences, and that is the input for this algorithm. So it's a ranking, so to speak, of the members of the opposite sex. The way this algorithm iterates is it forces each man in step one to propose to the highest woman on his list who has not previously rejected him. So when we start, and we'll see this in an example, when we start, all the men are proposing to the top name, and then we make determinations from that. If we're later on in the algorithm and the man has women higher in the list that have rejected him, we then skip those proposals until we get to the next one that has not rejected him. Each woman, upon receiving a proposal, she either accepts it or rejects it. In your book, it's going to say that the women say maybe. I'm going to refer to that as tentatively accept the proposal. So if a woman receives only one proposal, she accepts it. And then after that, if a woman receives more than one proposal, she rejects all proposals except the one from the man that's highest on her list. So, for instance, if Becky receives proposals from everybody in a specific round, she would reject all but Donald, because Donald is the highest name on her list. If Charlie receives proposals from Donald, Bob, and Cameron, she would reject all but Donald's proposal, because he is the highest name of the proposals that she got. Okay, so again, this algorithm is very sexist in the sense that it's written in view of the men proposing. The alternate view of having the women proposing also would result in a stable matching from this algorithm. But in order to, and I've actually gone through this same example with the women proposing multiple times, and based on these rankings, the matchings turn out to be the same. The process of getting there is obviously different. But just to make sure that we don't get confused in the language of the algorithm as well as the language of the proof, I'm going to stick with the men proposing to the women for our example. Our example here is going to be using the list of names that you've already seen, and we're going to find homecoming dates. I know a lot of us are high school teachers, and so we kind of see this on a daily basis, and this is kind of the perfect result of that. So let's start off, and we're going to have the first round of men proposing to women, or boys proposing to girls, whatever the case may be. So we have Alvin proposing to Charlie, Bob proposing to Charlie, Cameron proposing to Becky, and Donald proposing to Donna. So we look through here. Charlie gets 2 proposals, one from Alvin and one from Bob. Sticking with this proposal scenario, Charlie gets 2 proposals. She rejects all but the highest one. So she actually rejects Bob's proposal and accepts Alvin's proposal, as his name is higher on her list. Cameron proposes to Becky, and since that's Becky's only proposal, she tentatively accepts it, or as your book would say, she says maybe. Okay. Donna also only gets 1 proposal, that's from Donald, so she tentatively accepts that proposal. And after our first round of this algorithm, we have 3 pairings. Alvin to Charlie, Cameron to Becky, and Donald to Donna. As we take off on our second round, I guess a little bit easier to deal with as far as an example goes, we only have 1 boy that's not matched up with a girl. So we're just going to focus on that, and we're going to say, well, Bob is going to propose to Becky. Since Bob proposes to Becky, and Bob is higher on Becky's list than Cameron, she's going to leave Cameron or reject his proposal and end up going with Bob. That leaves Cameron unpaired. Now, to, I guess, kind of make sense of the algorithm, even though Alvin and Charlie are paired and Donald and Donna are paired, and they don't actually get rejected, we don't really worry about them in terms of this example, but in terms of the algorithm, the process of Alvin proposing to Charlie and Donald proposing to Donna would actually happen again, and Charlie and Donna would not would not say no. They would continue to go to the dance with Alvin and Donald respectively. So our round 2 results are that Alvin is still paired with Charlie, Bob with Becky, and Donald with Donna. So that the Bob with Becky is the new iteration of this algorithm. For the third step, we notice that Cameron doesn't have a date yet, so he's going to go propose to Charlie. And this is where it's important that in this round, again, Alvin proposes to Charlie as well. And Alvin's still higher on Charlie's list than Cameron is, so Cameron gets immediately rejected in his proposal to Charlie. And this is actually, even though nothing has changed, it's another round of results in that we have Alvin with Charlie, Bob with Becky, and Donald with Donna. Again, nothing changed, but we did try something else. We did try another iteration of all results. And what actually ends up being our last iteration, Cameron proposes to Adriana. Since she does not have any other proposals, she accepts Cameron's proposal, and they end up going to the dance together. Notice that through this process, all the boys got their top pick. Alvin got to go with Charlie, and Donald got to go with Donna. That's the top pick that they could get, and that's the top pick that they wanted. Bob and Cameron didn't necessarily get their top pick, but they got the best possible pick from the rest of the dating pool, and Becky and Adriana. The girls, on the other hand, realistically got their worst possible pick, with the exception of Charlie getting her top pick. All the other ones didn't get their top pick. They didn't. Some of them, didn't even get close, in the sense that Adriana's going with her third choice, but her other top 2 choices were already taken. So as you can see, our final results are Alvin is going with Charlie, Bob with Becky, Cameron with Adriana, and Donald with Donna. So from that algorithm, we come up with a theorem, and we're going to be proving that theorem. The theorem is that the proposal algorithm produces a stable matching. And we can see that as in all of these, Alvin was not paired with anybody that preferred that person over him, so to speak. Charlie didn't prefer anybody over Alvin. So that process produces our stable matching. And the proof goes as first just stating the fact that the algorithm is going to end at some point with some matching. And that's because, as we saw in those lists, mainly in terms of Cameron, because he got rejected the most, at every round of this algorithm, Cameron's total list, the length of Cameron's list diminished every single time. Okay, he got down to only 2 names on his list, and thankfully the second to last name said yes, and he didn't have to go with the bottom name on his list. So this algorithm will end at some point with some matching. And in fact, there are only going to be n squared rounds of proposals, at most, n squared rounds of proposals, because of the fact that there are n men and n women. So to prove that the algorithm produces a matching that's stable, we're gonna suppose the contrary. We're gonna go by contradiction here and say that the result isn't stable. So we're gonna let XA be an unstable pair. So what that really means is we have man X and woman A who really are attracted to each other, but based on our matching, X is paired up with, I'll actually write it in terms of of the pairing. X is paired up with woman B, and Y is paired up with A is paired up with man Y. So these are the actual pairings, but these two are really attracted to each other. In fact, they're each more so attracted to each other than they are to their current partners by the definition of unstable pair. So on the proof of this, man X, if this were the case, that XA is an unstable pair, man X never proposed to woman A. That's why they're not matched up together. If man X were to propose to woman A, since they prefer each other over the other ones, they would have been going to the dance together. They would be paired up with each other. But since they're not matched up, then they never propose. Then man X was never proposed to woman A. And because of the fact that every round of proposals, the man's list never goes upwards; it always goes downwards. So it's always descending, or at least staying the same. Because we said that, in terms of Alvin and Charlie, they were paired up right at the start, and they were each other's top choice. But Alvin had to kept proposing to Charlie, and so that makes Alvin's list technically never go down, but it never goes up either. So since the man's list never goes upwards, and the woman's list never goes downwards, she never gets because of the fact that she refuses all but her best offer, her list never goes downwards. That really means that man X would have never proposed to woman B without earlier proposing to woman A. So in essence, if we have man X's list here, in terms of this, it goes B, A, with maybe some stuff at the start and maybe some stuff at the finish, and even maybe things in between. So maybe we should say his ranking list here has some form of B, and then A, and then some other stuff at the end. That's how his list looks. Because of the fact that he's with B right now, but he really prefers A, that's our contradiction, that either his list was made incorrectly or what have you. It would actually, this is our contradiction, that man A would have never proposed to B without earlier proposing to A, making them not an unstable pair. So this contradicts our theorem that the proposal algorithm creates a stable matching. There's one real-time application of this in the United States where doctoral candidates, people that want to become doctors of medicine, go through what's called the match, and it's the actual name for it is the National Resident Matching Program, that pairs every that takes a look at all the residents, all the resident applicants, all the people that want to be residents in hospitals, and they list out their ranking of hospitals that they want to work at, and it treats the residents in our algorithm as the men, and the hospitals as the women, in the sense that the residents get to list off their hospitals that they want to work at. At the same time, the hospitals make a list of the residents that they want to work for them, and it goes through a residents first search algorithm of the Gale-Shapley algorithm, and pairs it up the right way. In fact, when this originally came out, it went with a hospital first list, and then they realized, hey, wait a minute, this is actually placing me where I don't want to be first, when there could have been an opening at a hospital that I wanted to be at. So that is my presentation on the Gale-Shapley algorithm, the proposal algorithm, to find a stable matching. Thanks for watching, and we'll see you later.